This is our code for a fixed point signed number that is added or subtracted to a stored result.
So here you can see we have the control switch. When set to 1, we will add. When set to 0, we subtract. This is our input. The input will be added to the stored result. So first, I will input 3, put 1 to the control, so we're adding 0 plus 3 because the result is not stored. We get 3, add 3 again. We get 6, add 3 again. We get 9, add 3 again. We get 12. The overflow was set the clock cycle after the overflow was detected. So now, to subtract 3, we go back down, we get 9, we get 6, we get 3, back to 0. Now I will do 0 plus 2. Oh, I did 0 minus 2 there, sorry. Back to 0. Now 0 plus 2. 2. 2 plus 3. 5.
This is the delay for our fixed point signed number adder and subtractor with a delay of 100 nanoseconds. This is our code for our complex operation with an FSM. So we have a start switch right here and a reset switch right here. We've got our P real inputs and imaginary, and then Q real and Q imaginary. And then LED 4 to 0 is our result imaginary, and 10 to 6 is the real result. So the first input is 1 plus J for P and 1 plus J for Q. So if we go through, we have the start switch on, and if we go through the clock cycles, okay, so the result should be -1 plus J, so that's showing there on the LEDs. Then our next example is going to be 2 plus J for the P and still 1 plus J for Q. So when we go through the clock cycles, it's going through the states. And this is the done indicator on this LED. So the result for this should be 2 plus 3J. So that is the correct result on the LEDs. Then the last inputs are going to be 3 plus 2J for the P and 2 plus 1J for the Q. So we should see 3 plus 11J for the result, which is what we have here. This is the measured delay for our complex FSM. The delay is 220 nanoseconds. This is the code for our sequential 4-bit subtractor with an FSM.
Here we have the reset switch, the start switch, our first 4 bits of input A, and our first 4 bits of input B. So here if I start it, do 1 minus 0. There we get 1. This is our done bit, meaning that the answer is, or the FSM is done running. So now we can do 1 minus 1. 0, that's correct. Now we can do 2 minus 1, or 1 minus 2. -1, that's correct.
This is the delay for our sequential subtractor with a delay of 400 nanoseconds. This is the code for our sequential 2's complement system with 10 bits.
So here, this is the reset switch, start switch, then our 10-bit input. So I start it, input 1, run through the states, that's the input, that's the complement of 1, and then it's storing the result in these next clock cycles till it gets done. Then I can input 3, it's no longer done. you can see that there's the 2's complement of 3. And then the next clock cycle store the result. Then I can do 5. There's 5. There's done. And then reset.
This is the measured delay for our 2's complement. The delay is 250 nanoseconds.